Wow, 13 minutes late getting started. I'm so sorry. But there will be no refund. Okay. We'll start from current slide. And before we get started on that, let me just go over these announcements in case you need to know them. I guess sometime today I have to enter midterm progress reports. Okay, it says on here I do. I saw nothing in the emails about them, so I don't know if they've opened it or not. But please get me something if you haven't got me a research paper, first test, something, so I can get a score. Okay. Let's see if there's anything else on here. For those who are interested, the Miss Lawson State coronation will be tomorrow evening at 7 o'clock next door in the Bessemer Civic Center. The print, black print on dark blue background, which is really hard to read. I can't read all of this. And for those people, and preaching to the choir here probably, but if you're on federal financial aid of any kind and you look like you are hopelessly behind in a course and no way you can pull a way out, it seems a little early for that, but if you did, the 60% completion date for the Title IV funds, which I think is all federal financial aid, is next Tuesday, which means that if you withdraw before then, you're going to have to pay back. If you withdraw after then, you don't have to pay back. Okay? And let's see, I don't see anything else of any major importance there. Volleyball team will be, let's see, this is coming up on the 18th and 19th. There is a tournament at Gadsden State Community College. The Gadsden State tournament will be coming up the 18th and 19th, which is Friday and Saturday in Gadsden, Alabama. So if you happen to be over there sometime Friday or Saturday, stop by and cheer them to victory. Okay? And I'll announce the rest of those later. Today is the deadline for your NASA's Community College Aerospace College Program. I saw that button before, but nothing happened. Today's the deadline, so I've got the information here. I won't have it after today. It won't be any good after today, so if you are interested, please get it and get it done. All right, any questions on anything we've done so far? All right, let's set up from our pen. And I think where we left off was Chapter 8, Integration Techniques and Improper Integrals, mostly integration techniques. 8.4 is trigonometric substitutions. That's what we've been working on, and we're on page 543, bottom half of the page, example 3. Now this example is also can be found at larsoncalculus.com, an absolutely free website. You don't need any codes or anything else to access it, and you can see an interactive version of this type of example. And here's what this example is. The integral of dx over x squared plus 1 to the 3 power. Okay. What would be your approach to that problem?
Wait, we're on example 3, right?
Example 3, right. Did I copy it right?
No.
No. Second. Page 543.
Oh, I'm in the wrong section.
Oh. Well, then get out. No, I'm sorry. Okay. All right. Second.
X squared is plus 6.
Yeah, I can't hear it.
Is the x squared plus 6?
Is x squared plus 6?
I mean, in parentheses.
This is the 1. Is that what you're saying? Yeah. X squared plus 1. Okay. The pen sort of drags sometimes. And this morning, one of the things I was fighting with, she was supposedly sent over something so I could sign it on my screen. would not work. But then finally I managed to do something and make it work. So, and it's an ugly signature. So anyway, it's not pretty. So what would be your first approach? Where would you begin? You think a U substitution will work? You let U be this thing in here. Then the du would be 2x dx. You don't have a 2x dx. So no, U substitution will not work. 2 is not important, but you got to have an x up there. So U substitution's out. What might be another suggestion? And which trig substitution would you use?
I think the second.
And which one's that?
The square root of a squared plus u squared. U equals a tangent theta.
Okay, so that's the one. And which trig substitution is that? Tangent. That's the tangent. I think of it because tangent squared plus 1 is secant squared. That looks like that. Okay, so let's let. So what will be the substitution once we get Fred here? That's the struggle always. We manage. Fred, you don't happen to have a sister here, do you? I saw a gal this morning, and well, I took a second look because I thought at first she looked a lot like you, but I thought, well, maybe. All right. What would be your substitution?
A is x squared.
Say that again.
A equals x squared.
A equal x squared? Is that what you said? I don't quite see where that's heading. Okay. Thought you said okay. With a trig substitution, okay, if you want to do it's usually you let the variable, in this case x, equal, what did you say the trig substitution would be? Is what? Tangent theta. Okay. Now, I think where the a may have come from, a would be involved if this was anything other than 1. Okay? This would be an a squared. But since it's 1, a is 1, so we don't need to even mess with the a. It's just 1. Okay? And then this is your trig substitution. That's the first step of it. Now, we got 2 directions we've got to head with it, so you tell me which way to go you want to go next. Second? I can't hear you.
You have to cube it.
Cube it. Okay. Now, did I write it? I think you just square it, don't you? Number 1, that's out of place. The x is just squared, right? So you square it. X squared is equal to, a little louder, tangent squared theta. Okay. Then what do we do with that? Add 1 to it. Okay. Now what? What is that? A little louder?
Oh, wait, that's a Pythagorean.
Yes, and what is that? Secant squared theta. Okay. Then we take a square root of that, and that gives you, pretty easy, secant theta. Okay. But we also got to do something else to it. Cube it. That's where the cubic comes from. You have to cube it. And I guess you could have earlier too. We'll see. Okay? Now, that's one leg. We've taken it about as far as we can there. What's the other thing you've got to do? You got x. Say again? You got x. I need something else. dx. Okay, what is dx? And I have to start with your trig instructor. Okay. It's the root of the tangent. That's secant squared theta. D theta. Excellent. Okay. I think we're almost ready to go now. Okay. So let's rewrite. And this will be the integral. And your dx is secant squared theta d theta over, and this thing, x squared plus 1, that was tangent squared plus 1, that's secant squared, square root of that is secant, cube that, so that whole denominator is secant cubed. Right? Yay or nay? Too much magic? Okay. Now, what does that simplify to be? One over secant theta d theta. Now, what is 1 over secant theta, though? That's cosine theta. Cosine theta d theta, and can we take that antiderivative of that? That's sine theta. One other little thing since we're missing plus c. Okay. But we started the problem in x's, we wound up in thetas. And one thing we forgot to do, and probably should have done at the very beginning, but it doesn't hurt to do it now, is what? Our little triangle. Okay, so let's draw a horizontal here, let's draw an angle here, and let's call a vertical here. And let's name this our angle theta, and we started off with x equal tangent theta. Now, I need a ratio there, so what could I put as my ratio? X over 1. Okay, now, tangent theta, what's the relationship of that? Adjacent over, tangent, opposite over adjacent. So that would be x over 1 and 1 down there. And then what does that make your hypotenuse? The square root of x squared plus 1, which is exactly what we had in our denominator to begin with. Okay? So that makes us feel warm and fuzzy, right? Now, the reason I need that is so I can now say, what in the world is sine theta? And what is sine theta? Yes, so that would be x over the square root of x squared plus 1 plus c. That seems to be it. Okay? And let's see what the book got. X over square root of x squared plus 1. X squared plus 1 plus c. All right. Now, they did a few other steps in there that we could have done or not, but anyway, came out the same. Right? Make sense? Any questions? Pretty exciting stuff, huh? All right. If no questions, move on to example 4. Yay or nay? Okay. Let's do example 4. So I'm going to erase what we got unless somebody's still copying or got it. You got it? Okay, let's get rid of that ink. For definite integrals, it is often convenient to determine the integration limits for theta that avoid coming back to the x. You can do it either way, but usually that's easier. Just like we did for u. If we did a u substitution, it's usually easier to go on and do the new limits for u rather than come back to x. But let's do it. They say You might want to review this procedure in section 4.5, section examples 8 and 9. That was, I think, when we did U substitutions. I believe so, anyway. So anyway, let's do this evaluation. Example 4. The integral from root 3 to 2, that's not a very big span there, is it? Of the square root of x squared minus 3 over x dx. What would be your approach to something like that? Any ideas? If that x in the denominator were in the numerator, U substitution, be a piece of cake, sort of, so to speak. I'd probably eat it, okay? However, it's not. So that doesn't look very promising. So what might we try? Anybody? All right, because this is a x squared minus something, that looks a lot like secant squared minus 1, which would be tangent squared. So yeah, except it's not a 1, okay? So what would be your substitution then? X equal, okay. Now we got a little bit of a problem here. We need that to be a 1, not a 3, okay? So there's a couple ways you can go about doing this. Here's how I like to do it because I don't remember where to put everything otherwise. I'm going to rewrite that radical as the radical of x squared minus 3. I'm going to write it exactly like it is, but divide this by 3 and divide this by 3, okay? Now, what that gives me is the square root of x over root 3 squared minus 1. Now that's ugly looking, isn't it? But isn't that what we got? Yay or nay? So, I don't know, you might not want to do it that way, but the key is that's a root 3 that we're dealing with. Now, how do our trig substitution go if you did have an a there? Maybe that's how I should have approached it rather than this way. Let's go back to this and say the square root of x squared minus 3. X is x, okay, or u or whatever you want to call it. The 3 is the square root of 3 squared, because your form is x squared minus a squared. So what do we do with that x squared minus a squared? Maybe that's how you prefer to do it. I don't know. You tell me. I'm giving you several options here. Probably just confusing you, right? Don't answer that question. Okay. Okay. X equal square root of 3 secant theta. That's it. All right. A sine theta. A secant theta. Okay. Now, we got a couple directions we can go. Which way you want to go? So forget about my stuff up here. I was trying to find ways to make it easier for you to see however you want to see it. Okay. And see, here's what I was getting at. And it's just my weird way of thinking. Remember when I had it like this? X over root 3 squared minus 1. When I had that, then I would have said let x over root 3 equal secant theta. And that one would have produced x equals root 3 secant theta. That's how I do it because I don't like to remember the a's and that kind of stuff. So I got the same thing. But however you want to do it, that's fine. Okay. This works. That's what we wound up with. So, what do we do next? We've got 2 tracks we need to follow. Actually 3, but it's a separate track. Okay. What do we do? Not yet. If you left out the root there, that would be fine. Square it. Okay, so let's do x squared. X squared is equal to 3 secant squared theta. All right. Then what? Subtract 1. Subtract 3, actually. Right? Okay? So subtract 3. All right, what do we do next? Now, your turn, Dawson. Say it again. Square root it. Okay, good deal. All right, square root this. That's what we got up that top. And we square root this. All right. Now, I'm going to simplify that a little bit. Maybe I should have done it before I square rooted it. I'm going to factor out a 3 out of what's inside, which means to factor out a root 3 outside. So those will be root 3 times the square root of secant squared minus 1. Do you see that, what I did there? What's that?
That's tangent squared.
And that's tangent squared. So this will be root 3 tangent squared theta. I left off my theta, didn't I? Okay. So, it's about as far as we can carry that one.
Wait, I meant tangent theta, not tangent squared theta.
Well, yeah. Under the square root, it would be tangent squared. Outside the square root is tangent. You're right. Good deal. Okay? Now what? That's going what I call the horizontal direction. We need to do vertical. What's that? Then, what else do we need? Help me, somebody. Help me. dx. And what is dx? Oh, this is a toughie, isn't it? Well, we don't use that much, but we've used it. What is that? I'm going to go and write the root 3. It's there. It's just a constant. What's the derivative of secant? Oh, I got to talk with your trig instructor. Don't fire that dude. That's it. Not squared. Secant theta tangent theta. Right? One more thing. D theta. Okay. Now, I think we've got everything in place. We need to start filling in the gap. Okay? Now, we really have 2 more things to do. But let's write down the integral first. Okay? But I don't want to write down those limits. Why? They're for ones for x. These correspond to x. Now we got thetas, so we need to deal with that. So let's go back up here and say we're going to be fiddling here. Do you want to do the lower one first or the upper one first? I really don't care, but give me one. Lower one. Okay, what we got here, x equal root 3. So we'll put root 3 is equal to root 3 secant theta. Right? Okay, so that means divide both sides by root 3 and you get 1 is equal to secant theta. Does anyone know what angle theta will produce a secant? Secant of that angle would be 1. What would the theta be? Okay, what is secant theta? 1 over cosine theta. So for 1 over cosine theta to be 1, what would theta have to be? 0, exactly. So the lower limit is 0 for your theta. All right? I'm going to erase because I don't have enough room to keep writing here. And then we're going to put a 2 here. Whoops, I erased too much. All right, we'll fill in the blanks later. All right, what we got now is 2 is equal to root 3 secant theta. So what would we do then? Divide both sides by root 3, just like we did before. I didn't have to erase that, did I? These go out, but those stay. What we have now is 2 over root 3 is equal to secant theta. Now what I suggest is flip them both. What would that produce? Yes. Root 3 over 2, which is cosine. So what angle theta will give you, if you take the cosine of it, will give you a root 3 over 2. Pi what? Pi 6, exactly. So for theta, we're going 0 to pi 6. See how we got that? Know your trick. Okay. Now let's fill in what goes on the inside. This radical here, which is square root of x cubed x squared minus 3, that's this thing right here. I'm pretty sure that's this thing right here, and that wound up being this. That's going to be a root 3 times the tangent of theta. Right? Yay or nay? What you say? Yeah, got it. Then we got our dx, which is another root 3, so that makes it just a 3 out front. A secant theta times another tangent theta, so that's tangent squared theta, and a d theta. Got that one? See what we did? Because our dx, see we had this part, then we had this part, and the dx was that. The square root was that one. But then we got our denominator here, and that's an x. What in the world is x? 1 over root 3, so now this goes back to being a root 3 again. Okay? I could have done that a little nicer. Secant theta, right? Goodness gracious, what is all this mess? I think I've got it all in place, don't I? Yay or nay? The radical was the root 3 tangent theta. The dx was root 3 secant theta tangent theta. And the denominator x was root 3 secant theta. What can you do now? Help me, somebody. I'm drowning. Yes, the secants divide away, right? And now we're left with the integral of tangent squared theta. Oh, a big boo hiss here, isn't it? What in the world is tangent squared theta? We're going to have to go back to, where we are, what we had before. Maybe or maybe not. Let's use our good old square root of 3, okay? Integral from 0 to pi 6. Now what do you notice here? What is tangent squared theta? Secant squared theta minus 1. No, plus 1, right? No, minus 1. Secant squared theta minus 1 d theta. Now, let's make that two integrals. That would be root 3 times the integral from 0 to pi 6 of secant squared theta. Now, is that any better than tangent squared theta? D theta minus root 3 times the integral from 0 to pi 6 d theta. Didn't we just trade one square for another square? Did that help us any? Help me.
We can take the derivative.
Yes, this is a perfect derivative. That is not. What's this a perfect derivative of? Tangent theta. So what we have here is root 3 tangent theta, okay, evaluated from 0 to pi 6, okay, supposed to be a line there, minus root 3, and what's antiderivative of theta? D theta. I said it. Theta, evaluated from 0 to pi 6. Okay? So let's start. I'm going to pull out that root 3. I'm tired of hauling it around. Root 3 is out front. Okay, I'm going to fill in the blanks here. What in the world is the tangent of pi 6? Square root of 3. Is that right? Seems a bit large. You may be right. Yeah, I believe you are right. Okay. No, you're not. Okay. Because tangent of pi force is 1. So tangent of pi 6 has to be something less than root 3. It would have been nice, wouldn't it? Really nice, but no. You can't make up stuff. Okay. Tangent of pi 6. Well, isn't that 1/2 over square root of 3 over 2, which is 1 over root 3, or root 3 over 3, or however it is. So let's do a 1 over root 3. I like that kind of because of what comes next. Minus, and what's the tangent of 0? Ooh, isn't that nice? Okay. All right. Then we have another minus. I already pulled out my root 3. Okay. And when theta is at pi 6, you got pi 6 minus 0. So that's what I think we have as an answer, which I think is 1 minus root 3 over 6 times pi. I hope that's it anyway. Oops. They say it's a minus 1 with a plus. Now, how did they do that?
No, that's right.
Oh, I'm on the wrong page. Okay. Yes, we got it right. I was going to say, how in the world did they get that? I was looking on page 545, which has exactly the same answer, just reversed, the negative of it. All right. And guess what? What did we leave out? One of our favorite things to do. Our little triangle. Once we didn't go back to the x, we didn't need it anymore. Once you figured out what the limits were, you didn't need the triangle anymore. That won't necessarily always be the case, but it was in this one. Okay. Now, it says in example 4, try converting back to the variable x and evaluating antiderivative at the original limits of integration, you should obtain this, and it says you don't. Okay? Well, let's see. When using trigonometric substitution to evaluate definite integrals, you must be careful to check that the values of theta lie in the intervals discussed in the beginning of this section. Oh, okay, I see what they're saying. Okay, sorry about that. This is a new problem here. That one is perfectly fine. But they're saying if you had had from -2 to negative pi thirds and had tried doing the same problem, you would have gotten a negative answer. And what you have to worry with then is the fact that x squared x squared minus 3 has to stay positive because you can't do it without it. And if you had plugged in those values, minus root 3 squared would be a 3 minus 3 would be a 0. If you plugged in the minus 2 and squared it, that would have given you 4 minus 3, which would have been okay. But the problem there is that the root 3 is greater than, negative root 3. I'm not sure what they're getting at here, okay? Okay. It's a lot of blah 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 there. I think it's okay. I think I see what they're getting at, but their example leaves a little bit to be desired about the thing. You will come up with a negative answer, and that usually means you're something below the x-axis. So I think that's going to be the case here. So I really don't think you have to worry about it. However, there still may be something else. So let's move on. We did ours right. That was the important thing. No, they still are leaving this out. It says trigonometric substitution can be used with completing the square. And I don't know why they left that one off. So let's go back. Let me clear the screen here, because this is something important. Now, why they left it off the slideshow, I'm not sure. What if this had been your integral? This is integral of the square root of x squared minus 2x dx. Okay? If you didn't have the x there, that would be okay. You could do a trig substitution. Okay? If you had some number out there, that might have been okay too, but you don't. But this won't work with a trig substitution. It sure won't work with a U substitution. So you may think you're dead in the water, but their suggestion is complete the square. So that would be the integral of the square root of x squared minus 2x. How do you complete that square? Anyone remember that? Oh, come on. You've done it so many times in your life. Half of the b, which is -1, square it, you get a +1. But you just changed the problem. You put a +1 in there, you also got to put a -1 in there, so you don't change the problem. Now that seems ridiculous, doesn't it? Don't answer that question. Okay. Now, pair this part off. There's your perfect square trinomial, right? So now we have, and that's exactly the same as above. That's the square root of x minus 1 squared minus 1. What you notice here now, this is a secant form where secant theta is equal to x minus 1. So it's a little messier, but it's still doable. So secant theta is equal to x minus 1. And you continue going. I left off my dx, and that's what they say to go with it. That has the form of square root of u squared minus a squared, where u is x minus 1, a is 1. All right. Done? All right. Now we'll go to the next slide. Trigonometric substitution can be used to find the three integrals in the next theorem. These integrals will be encountered several times. Promise or threat. Okay? Special integration formulas. This is the square root of a squared minus u squared. What do you reckon that's going to be? What substitution would that be?
It's
Sine, because 1 minus sine squared is cosine squared. So that would do quite well, except it's now a sine. Okay, now. Why do they have that as if you need to remember that? You just do the substitution. So this one, what would that be?
that's our secant.
Secant, okay. And this one? Tangent. And you notice, well, you don't notice, do you? You see an arc sine in this one, but you don't see it in either of these two. So it's a big boo hiss here. What in the world are they doing with this thing? All right. It says these integrals will be encountered several times. So you might want to jot these down so you can go back to them. But I think you can work them out and you don't have to have this done for you. But you can always look them up in a table. But they just leave it like that. Then they do an application. Okay? So let's do the application. Find the arc length of the graph of f of x is equal to 1/2 x squared. From x equals 0, to x equal 1. So there is the graph of that. Here's your function. You want the arc length from 0 to 1. At 0, it's 0, of course. And at 1, it's 1/2. So when x equal 1, f of x is equal to 1/2. So yeah, that looks good. It's a parabola, one that has a vertical shrink. That's the arc length you want. Now, do you remember how in the world you do the arc length? Oh, wait, we're through with that, aren't we? No. How do you do arc length? Oh, man. Long time, wasn't it? Remember what we called arc length? S. S is equal to, okay. Anyone remember?
I know it's an integral.
Okay. It's an integral, and it'll be between 0 and 1, because that's where we're going from. Okay, it's the length.
Wait,
So,
is this the one where
yes.
you take the derivative of x?
Yes, take of f. So f prime of x, that's your first step, and that is x, okay? And what do we do with that derivative? Square it. So f prime of x squared is equal to x squared. And then what do you do with that? Add 1 to it, okay? Okay, I've done it. And then you do what with that? Then you take a square root of it. You got it. Hey, the old memory, the old great cells, they are what they used to be, right? Okay. Now, and that's your integral. Now, I was going to say, think length, distance. That's basically your distance formula, okay? Whereas, in a sense, that's where you got it from. So, this will be times dx. So, this will be the square root of x squared plus 1 dx. Agreed? How do we do that? What?
It's our secant form.
It's what?
The secant.
Not secant. Secant is x squared minus 1.
So this one's the tangent.
Is tangent form. Okay. It gives you a secant. So we'll let, and what would it be then? Say it again. X equal tangent theta. Okay. It's 1 tangent theta. Let's leave off the 1. Okay, we got 2 directions we have to go. Which way do you want to go first? Second square, is that what I heard? Okay, so we'll first go this way and square it. So x squared is equal to tangent squared theta. Okay, and what do we do with that then? Add 1 to it, so we'll add 1. And then we do what? Take a square root. What is tangent squared theta plus 1? Secant squared theta, that's where that came from. Now we'll take a square root of that, and that gives you secant theta. And I think that's as far as we need to take it, right? Let's go down the other way, and what do we need to do? Dx is equal to, help me, derivative of the tangent.
Is it secant times tangent?
No, that is what?
Is secant theta times tangent theta?
That is the derivative of secant theta. Secant squared. Secant squared theta d theta. All right, I think we're ready to roll now. This will be, ooh, not quite. When x is equal to 0, what would theta be? X equals 0, what would theta have to be? Also 0, okay? And when x is equal to 1, what would theta have to be? Pi what? Fourth. Perfect. Okay. So we got our limits straightened out. Okay, the x, the radical thing here is secant theta. I can't write. Secant theta. That's the square root of 1 minus of x squared plus 1. Okay. And then your dx is another 2 secant theta, so that makes it secant cubed theta d theta. All right. Now, at this point, you can either go back to your previous section, section 8.3, I believe it was, the trig integrals, and go back and figure out how in the world to do that. And that's perfectly fine to do. Or, far easier, is to see if we got it in the table. And unfortunately, your table only does secant and secant squares. So that's not helpful, the front table. the back table, I have a feeling, will be a lot more forthcoming. And that's, I thought I had it marked. Oh, I do, but I was in the wrong part. Involving, okay, these in your back of the book, this is in Appendix B, page A5. That's in front of the index, in front of the answer to your problems and stuff like this. A5, at the bottom of that A5 is forms involving tangent use, cotangent u, secant u, and cosecant u. Well, this is a secant u. It's a secant cubed u, and they don't show you secant cubed u, but they do show you secant to the nth u, right? That's number 69. So let's write down what we've got here. I need something holding my place, okay? What we have here is, maybe it'd be easier to just go on and do the thing. This would be secant to the n minus 2. Well, n is 3, so n minus 2 is 1, so that'd be a secant theta. Okay, I'm not using u, I'm using theta. Times tangent theta. Okay. Over n minus 1. N was 3, so this is over 2. Okay. Plus, here we have another integral coming up here. n minus 2, which is 1, over n minus 1, which is 2. The integral of secant theta, because it's secant to the n minus 2, n was 3, so it's secant theta d theta. And this is evaluated from 0 to pi fourths. Now, something you have to do here is also evaluate this one from 0 to pi fourths, because you are evaluating these things. So we plug that in because that's already, the integration's been done for you, so you have to plug that in there. Okay, anyone remember what the integral of secant is? So what I'm going to do is pull out my 1/2s out in front, because they're 1/2 everywhere. Okay. Anyone remember what secant of pi fourths is? What is secant? 1 over cosine. What is cosine of pi fourths? Is what? Okay. Secant is square root of 2. Cosine would be square root of 2 over 2. Yeah, so this would be root 2. That's the secant of pi fourths. Tangent of pi fourths is, is what? 1. So you just got a root 2 there, minus the 0, and secant of 0 is 1 over cosine of 0, and cosine of 0 is 1. So that would be 1 times, but what's tangent of 0? 0. Okay. So we just got a root 2 from that first part, plus, now, I've already pulled out the 1/2. What's the antiderivative of secant theta? Okay. Well, since you're already back there in your appendix anyway, appendix B, page A5, there's secant right there. And this is that weird one. It's the log of secant theta plus tangent theta. Natural log of absolute value secant theta plus tangent theta. Okay. We don't need the plus c because we're evaluating. We've got our limits. So we'll evaluate this from 0 to pi fourths. All right. Now, the root 2 doesn't change, so don't worry about that one. secant of pi fourths was, so what I have is a 1/2 root 2 plus the log of absolute value, what's secant of pi fourths? Square root of 2 plus tangent of pi fourths, 1, minus, okay, I think I'll end that one and do a minus the log of, and secant of 0 was 1 plus 0. Okay, and what's, that's going to be 0 because the log of 1 is 0. So this goes to 0. Okay, I think that's our answer now. So let me write it somewhere here. 1/2 of root 2 plus the log, and since root 2 and 1 are both positive, log of 1 plus root 2. I just like it that way a little better. Okay. Now they, I think, probably plug in some values there. Let's see if they do. They get 1/2 of root 2 plus log of root 2 plus 1 plus root 2, whatever. And they say that's about 1.148. Y'all got it? I'll take their word for it. All right. So in that case, we did use, because we had there something just like number 3 here, and that's what we did. But goodness, it was just about as easy. I mean, if you had to look that thing up anyway, why bother? You know, it wasn't hard to get. You did have to look up the integral, but you see how they came up with that. Okay. So let's see how they did it. Refer to the arc length formula, which is S is equal to integral from 0 to 1 of the square root of 1 plus f prime squared dx. And that would be the integral from 0 to 1 of square root of 1 plus x squared dx, exactly like we got. And magically they get this. We worked through it and got that. The integral from 0 to pi 4. See, they did their change of variable. They did all the mess there. Skipped way too many steps. And then they're doing something I don't. They're skipping a lot of steps again. That's the only thing I can say. They went and found their formulas or whatever, skipped a whole lot of steps. There's no way you can go from this line to that line without doing something else. Even looking up in a table, it's going to take something to go there. So they did it, and that gave them our answer, which is approximately 1.148. They're skipping example 6. Of course they would. It's a pretty tough looking example. So let's see if we can tackle it. How are we doing on time? Are we okay? Yeah. Okay. Comparing two fluid forces. A sealed barrel of oil weighing 48 pounds per cubic feet I don't like the way they worded that. If you said weighing 48 pounds, that makes sense. But they should be saying with a density of 48, a weight density of 48 pounds per cubic foot. That makes sense, okay? But anyway, it's floating in seawater weighing 64 pounds per cubic foot. Again, that should read having a density of 64 pounds per cubic feet. This is pretty sloppy on their wording here. as shown in figure 811, which they don't show, of course. And then later, 812. The barrel is not completely full of oil, and with the barrel lying on its side, the top 2/10 of a foot of the barrel is empty. All right. Compare the fluid forces against one end of the barrel from the inside and the other from the outside. Compare the fluid force Okay, I already read that. Assume that the radius of the barrel is 1 foot with the barrel lying on its side. The top 16, okay, I got it. I was going to say, they've already said that, but no. With the barrel lying on its side, I think that should be a semicolon there. The top 6/10 of a foot of the barrel is above water. Okay. Now, thank goodness they've done a lot of the drawing for you. Okay? I'm not going to draw that first one. You have to look in your book to see that. But I will draw the second one because that gives your coordinate system and everything else. Let's suppose that's our circle. Okay. Now, they're letting the coordinate system be the center of the barrel. That's going to be the origin. Okay. And this is a 1 foot radius. Is that what they say? Yeah. Radius of the barrel is 1 foot. So this is the point. Goodness gracious. 1, 0. This will be 0, 1. This will be -1, 0. And this will be 0, -1. Okay. In that coordinate system. Okay. Now, some of the things they tell us, going back to the thing, the barrel is not completely full of oil, with the barrel lying on its side. The top 2/10 of a foot of the barrel is empty. Okay, so the oil is up here. So this height here will be 0.8. All right. 0.8, was it feet? I think it was. Yeah, foot. Okay, that's that point there. Now, the water level, okay, let me read on down. The top 6/10 of a foot of the barrel is above water. So that means the water level is about here. Okay, so this will be 4/10 of a foot. All right. I think that's their picture pretty much as you see it here. And they do one other thing. The barrel itself, since it's a radius of 1, is x squared plus y squared is equal to 1. All right. Okay. Trying to recall. guess you, yeah, okay, it's all doable. I was going to say, they don't do the integration. They say the details of the integration are left for you to complete as exercise 64. And I see no reason, I mean, I'm trying to see why they do that, because I think it's all fairly much doable, but it's tedious, to say the least. With the densities and everything else that's involved here, it's going to be very, very tedious. And what's more, they're using weight where they should be using density. And that is also going to be messy because they're not really doing it properly. So I would say let's just can that example 6. It's a really involved problem. Not a bad one to you work through on your own. And they give the general equation from back in 7.7, so you can go back there and check, but sure enough it is. Oh, now that I think about it, I think what they were calling W back then was weight density. They keep calling it weight, but it's weight density, okay? So that is correct then. They've got it in here correctly. W is your weight density, because they have it written down. That formula is density times height times length. So that is correct. They called it wrong up above, but they got it right in the formula. Okay. So, but still, it's going to be really tedious getting it done. All right. So let's leave that one and just go on to homework exercises. 8.4. Do any of the either 3 or 5, they're both a Calc Chat. Either 7 or 9, they're both a Calc Chat. 7's a Calc View. Either 11 or 13, they're both a Calc Chat. Either 15 or 17, they're both a Calc Chat. Any of the odds 19 to 31, they're all at Calc Chat. 19's a Calc View. 33 or 35, they're both a Calc Chat. 35's a Calc View. 37 to 41, they're all at Calc Chat. 37's a Calc View. And you can explore doing either 43 or 45. They're should be both a Calc Chat. There are a couple true false, 47 and 49. They should be at Calc Chat. Then there's an area problem, 51. That should be at Calc Chat. An arc problem, 53. That should be at Calc Chat. The volume of a torus, 55. It should be at Calc Chat. A centroid problem, that's 57. Should be at Calc Chat. And then any of the odds 59, 61, 63, 65, 67, any of those you can do, and that's a Calc Chat. They should all be a Calc Chat. I was trying to see. Ah, 64 was one we weren't assigned because it's an even problem. So I was trying to see if we hit the one they were talking about, but no, we didn't. Okay. Any questions on section 8.4? Let's move on to 8.5. Now, did any of you need to see, if you really want to see that one done, I I think we can do the integrals. They're not that bad. A little bit of messiness with the numbers, but they're all numbers and they're doable. You want to do it or not? You want to see it done? It's up to you. If that's the type of problem you're really interested in and you want to see how that happens, we can do it. What you think? Second? Okay. Thank you. I'm all in favor. Because it would just take probably most of the rest of the class time. All right. So let's get out of this. I think we've been trying to get out of it for a while here. There we go. That's not what I wanted. Why did it go there? It says click to exit. There, that's what we needed. I guess my cursor was on something it shouldn't have been on. Okay. So let's move on to 8.5. I don't know why I'm so starving this morning, but I am. Had regular breakfast and everything. PowerPoint found a problem, blah, blah, blah. Can attempt to, so let's see if they can repair it. I didn't know there was a problem. I don't think there really is, but let's see. This isn't looking good, folks. Oh, there it is. It is looking better than I thought. Okay, let's see what this says here. Protective View Office has detected problem. File editing may harm your computer. Click here for more details. Let's just see if we can live without it. Okay. All right. Integration techniques and improper integrals. I saw those fish in one of the examples we had for this time. I remember the stars from before. Let's move on to partial fractions. So, your objectives here are to understand the concept of partial fraction decomposition. We're going to start decomposing some stuff. We'll use partial fraction decomposition with linear factors to integrate rational functions. And then we'll use partial fraction decomposition with quadratic factors to integrate rational functions. And you might say, do you need any higher? And we'll see, no, you don't. You can get everything to those. So, a procedure for decomposing a rational function. Now, what is a rational function anyway? Remind me, what is a rational function? What's the first 5 letters? Ratio. What's ratio? Yeah, fraction, division of something. What are the somethings for it to be a rational function? What's in the numerator? What's in the denominator? Polynomials. A rational function is a ratio of 2 polynomial functions. Okay? So a procedure for decomposing a rational function into simpler rational functions to which you can apply the basic integration formulas is called the method of partial fractions. To see the benefit of this method, consider this integral. You think of any way you can integrate that. U substitution is not going to do you any good. If you let the denominator be your u, your du would be 2x minus 5 dx. You don't have that in the numerator. Now, could you in some sort of convoluted way complete the square down here and get something that almost looks like either a tangent or a secant substitution? Maybe, but I sure don't want to try it. Okay, it will be messy. There is an easier way to do this. Now, just looking at that denominator, does it look like anything that we might be able to do with that? Factor it. And it does factor pretty nicely, in fact. Okay, so how does that factor? Whoops. I've got to get for some reason, this is such a pain in the neck.
It's because it said that you couldn't edit it.
What's that?
Yeah, it said that there was a problem with it and you couldn't edit it.
I think it has something to do with it. How do I get around it? See, all it gives me is a laser pointer. I don't want a laser pointer. I want my pen. Give me my pen back. Now, I think the only way I've managed to do this before is to start over and reboot the...
You have a marker?
Huh?
You have a marker?
You mean a mark on the board? We could do that. I don't have one in here. I guess the instructor that's before me must bring hers and take them away.
Yeah, because she has to use the
What's that?
She has to use the board.
She what?
She had asked if you used the board and we told her no.
Oh, I do have a marker. And what did you say again? I couldn't hear.
She had asked earlier if you used the board and we told her no.
She asked if I used the board. Oh, when you came in, because she was going to leave some markers? Okay. And you said no, we didn't use it? No. See, he's a problem now. Okay. Now, do you want to do it that way? It won't be recording for the rest of the students, but y'all don't care, do you?
They should have been.
Yeah, they should be here. Okay, I thought that's what I was hearing. Okay. Well, I'll talk, and maybe they can do it themselves. You don't want me to try to reboot PowerPoint. Y'all are mean. Okay, let's do it. Okay. All right, I'm all in favor. They should be here. Okay.
We only got 10 minutes.
Yeah. How does that factor?
X minus 2,
X minus what?
2 and 3.
3x minus 2. Is that what you said?
Yes, sir.
Yeah. Everybody agreed that's how it works. Okay. Now, here's the key to what we're going to be doing here. We're really messing just with the rational expression, not really with the integral yet. We're going to take this rational expression here, 1 over x minus 3 times x minus 2. And we're going to say, we think this can be broken down into an a over x minus 3 plus a b over x minus 2. Is the rationale for that? If you were indeed trying to add these fractional forms, the least common denominator would be the product, right? Right? And then you could manipulate this, you multiply this one by that and this one by that, add them together and see what you get. Now we're going to do it a little bit easier way than that, but that's exactly what we're going to be doing. Now here's the easier way. We're going to multiply both sides of that equation by this denominator. Okay? So we're going, okay, done. Multiply this by x minus 3 times x minus 2. Multiply this by x minus 3 times x minus 2. And multiply this by x minus 3. That's a 3 times x minus 2. You're beginning to appreciate the marker or the other thing, aren't you? I really write lousy with markers. Here, this goes out and this goes out. That leaves us a 1 here. Hey, I can handle that. Okay, over here, the x minus 3's go out, and you're left with the a times x minus 2, right? Here, the x minus 2's go out, they've been dating, and you get a plus b times x minus 3. All right. Now that's what we would have had we combined, that's what I've done is exactly what I said. Multiply this by x minus 2, multiply this one by x minus 3, and then the denominators are the same. Now we're making the numerators equal. Okay. Now, you could do this and do 2 equations, 2 unknowns, or something like that, and that might be a little messy. There's an easy way. Can anyone know what that way is? It really doesn't seem fair, but it works. What? trick is, and it's a trick in my mind, is let's just say let x equal 2. Now why would I do that? That becomes a 0. So when that becomes a 0, what do we have here? 1 is equal to x equal 2. That goes to 0. This goes to
0 plus
second
-1.
minus b. Right? Guess what b is then? -1. Okay? And if that, since that works so well, let's do it again. Only this time, let's let x equal 3. And what does the left-hand side become? 1, there's no x on it, is equal to, and then you get a. Right? Because the other one's 0. Okay? Now, with that in mind, let's go back to what we had here. This would then be the integral, and instead of this form here, which is that over that, we're going to write this one. I want to write the positive first, so that's going to be integral of 1 over x minus 3. That's a over x minus 3 dx minus the integral, because this is a minus 1 here, b is minus 1, integral of this right here, 1 over x minus 2 dx. Can you do that integration? Please say yes. Anybody?
Isn't it
Natural log of
x minus 3?
x minus 3. Usually put it in absolute value bars. Minus
Natural log
the natural log of x minus 2. Okay? Now, and then you probably want to plus c somewhere out there too, right? Okay. I'm going to hold off on that for a moment. Okay? I don't know if you remember the rules for logarithms. This is the same as the natural log of x minus 3 over x minus 2. We can put the absolute value bars over the whole thing there. And then we can either do our plus c there, or maybe if you wanted to, you could say log c. That's just a constant 2, right? And then you can multiply this by that and have a c in here. But that, I don't think, is what they do. 10 o'clock scholar, good deal. Okay. Okay. Oh, super, thank you. Okay, what you got?
You want to staple it all together?
Yeah, you can, whatever you want to do. You could staple once or just put it inside, or staple twice, or whatever. I'll usually hang on to it once they're inside. Or you can, yeah, staple again. Yeah. All right, good deal. Thank you.
Thank you.
All right. That's just for showing up. All right. Makes it look better anyway. So, I don't know if they wanted us to carry it that far. We did. Let's see. I believe, if I'm not mistaken, we just did example 1. Okay? And all it asked for was write the partial fraction decomposition. It didn't ask you to integrate. We integrated, so they don't give an answer for that. Okay. We did more than they did. Okay. Oh, I'm sorry, wait. No, they did. On page, well, let's see. They may do it on the slide here too. To find this integral without partial fractions, you can complete this. That's what I was saying. You could do it that way. Who wants to? Not I. Okay. So they did do that, carry through, and look what they got as an answer. Log of absolute value x minus 3 minus the log of absolute value x minus 2 plus c. That's the answer they got that way. Now, here's the answer they got this way. Like I just said, that gave us log, whoa, much easier this way, okay? And they just said plus c, they didn't do plus log c, okay? The method is clearly preferable to trigonometric substitution. Agreed? Yeah, yes. Its use, however, depends on the ability to factor the denominator. If you can't factor the denominator, you may have to use completing the square, okay? But if you can, find the partial fractions. We know that from algebra, every polynomial with real coefficients can be factored into linear and irreducible quadratic factors. You knew that, right? It can, okay? For instance, even if you had something like that, it can be written as, now that one's actually pretty easy because you can factor by grouping. And I think we're out of time, aren't we? To see well. So we'll start at the top of page 551. And since we really didn't do any examples yet, there won't be any homework exercises here. That's where we'll start there. And hopefully next time the pen will work. But y'all don't care, do you? Okay. All right. Good deal. Let me end the